Hola amigos, so let's continue with thrust available with maximum velocity and power required for level and unaccelerated flight. And let's see a little bit of thrust required, which we left in the earlier lecture, that thrust required variation for different velocities is given by this, and thrust required minimum is this point. Okay, if you observe this curve, thrust required minimum is this, and drag polar curve from the first lecture of this chapter is given by CD and CL variation, like this parabolic variation, and the intercept is given by CD naught. It is basically actually for preliminary design considerations, and it is a standard graph which we will be using every now and then in this chapter. And the drag coefficient for zero lift CD naught varies with velocity, like this, that it keeps on increasing with velocity. The zero lift drag keeps on increasing with velocity, and this induced drag, this dashed line which is coming down, is this induced drag coefficient which keeps on decreasing. So there is a point of intersection, this, where induced drag and the zero lift drag coefficients are equal, and induced drag is equal to KCL square. So why does the induced drag keeps on decreasing? CD naught, we can say it is increasing because the aircraft, when keeps on increasing its velocity, the drag will increase because of the resistance of the air keep on increasing on the aircraft body. But if we observe this induced drag coefficient, it means that as the velocity is increasing, like I said, for a steady level flight where we have to maintain lift equal to weight and thrust required equal to drag, there we have to say that if we increase the velocity, we have to decrease the coefficient of lift, CL. So we know from this relation also, if velocity increases, the CL will decrease. So when the aircraft velocity will decrease, the CL should increase. Okay, so here we can say the CL is maximum, or here we will say that CL is quite low. Okay, so how we can say that here velocity is high, therefore CL should be minimum, and here velocity is minimum, so CL should be high. So on relating it with induced drag coefficient CDI, which is equal to KCL square, so CL is low over here. As velocity increases, CL will increase. Sorry, as velocity increases, CL will decrease. So CDI, which is KCL square, will also decrease, and the intersection point here is CD naught equal to CDI, which is equal to the KCL square, and from here we can find this coefficient of lift or induced drag coefficient. And one more thing here is that it is at coincidentally it is at thrust required minimum, which is the design point for an airplane to perform optimally. That is, L by D or CL by CD should be maximum. From there we got this result, CD naught equal to CDI, for thrust required to be minimum. Okay, so now let's move on to thrust available. Thrust available, it depends upon the type of engine that is installed on the aircraft. For a given aircraft, okay, if we say the aircraft is this and we just need to install our engine, we have jet engine and propeller engine, and let's say the aircraft is installed with first jet engine, and we observe the thrust required is this. Okay, the amount of thrust required variation with velocity is this, and when we install propeller engine on the same aircraft for the same layout, and at the same place we install the propeller engine, then also the thrust required to overcome the same amount of drag experienced by the same design of the airplane will be the same for given velocities. Okay, so which is why the thrust required variation is always the same for a given design airplane. Okay, and only the thrust available variation is there for different type of engines on the airplane. So thrust available depends upon the type of engine on the airplane, and it varies for propeller like this, that it keeps on decreasing as the velocity increases. That is, thrust available keeps on decreasing as the velocity increases, and there is a limit which is Mach number equal to 1, or say sonic speed is the limit up to which thrust available can go. Okay, it should be less than the sonic speed always. The aircraft should fly always less than this velocity, so that it should not exceed this sonic speed, which is, sonic speed is when the aircraft attains the velocity which is equal to the sound of speed of sound. Okay, that is, the speed of sound is equal to the speed of aircraft. At that point, the Mach number reaches 1. You will learn this concept majorly in aerodynamics, so don't worry if you don't digest this for the timing. Just know that after reaching this velocity, or on exceeding this velocity, the aircraft will experience high drag because of the phenomena of shocks. As the aircraft exceeds this velocity, the shocks keep dragging the aircraft with the waves that come along while exceeding this velocity. Okay, so the wave drag, as I said, will not be considered because we are observing the airplane performance for subsonic flights, which are Mach number less than 1. So thrust available variation is like this, which keeps on decreasing for the given velocities for propeller engine, and thrust available for a jet engine is quite the same, or say constant, for different velocities. Okay, and the last thing is for thrust available and thrust required is that thrust required, as I said, only depends upon the layout of the airplane, and for a given airplane with any set of engine, whether it has jet engine or propeller engine, the thrust required will remain the same for given velocities. For any engine, whether it's jet engine or propeller engine on the airplane, the thrust required will be same, because it just have to overcome this much amount of drag, because thrust required is equal to drag for a steady level flight. So the amount of drag it has to overcome, the aircraft has to overcome, is only dependent upon the design or layout of the airplane, which should be equal to the amount of thrust required, and whose variation is given by this parabolic curve. And if we superimpose these thrust available curves of propeller engine and jet engine, we can see they intersect with the thrust required curve for the same aircraft, but with different engine. The thrust required is same, but thrust available is different. Okay, thrust available for jet engine is this, and thrust available for propeller engine is this, decreasing. So where they are intersecting, the thrust required curve gives us the maximum velocity that a propeller engine can make the same aircraft fly, and the jet engine can make the same aircraft fly. Aircraft is same, which is why the thrust required is same, but the thrust available is different, which is why this propeller will make this airplane fly at this much maximum velocity, whereas the jet plane can fly at this much maximum velocity for the same aircraft we are talking about. So moving on to the power required for level and unaccelerated flight, we will see that power required is equal to the amount of thrust required, or the force required, multiplied by the velocity with which the aircraft is flying. And thrust required is just the drag which has been substituted in terms of non-parameters, and like earlier we did for thrust required, which is equal to drag multiplied by lift divided by lift. Similarly we did over here and formed this formula for power required, which gives us the result that power required is inversely proportional to the CL raised to power 3 by 2 by CD, and power required will be minimum at CL raised to power 3 by 2 divided by CD maximum. And if we see this in terms of drag, we can divide it like we did for thrust required. Power required in terms of zero lift power required and lift induced power required. Okay, so based on this, like we did for thrust required, we drew the graph of power required and velocity variation for power required at lift equal to 0, and this power required for lift induced. Okay, and they are intersecting at CDI equal to CD naught, and we know that power required is varying with a relation of V cube, because drag or thrust is directly proportional to the V sphere, and V sphere when multiplied by V will give us V cube. So power required is directly proportional to V cube. They both have the same amount, same curvature, but the amount of curvature for this thrust required is less than the amount of curvature for this, because this is square and this is cubic. So as we did for thrust required minimum, to determine the CL at which an aircraft should fly, or the velocity with which the aircraft should fly, here we have also done the same thing to maintain this power required minimum to fly our aircraft optimally, or to perform optimally. The aircraft should fly at power required minimum, which is at CL is about 3 by 2 by CD maximum. And from this we can find that for what CL is about 3 by 2 by CD is maximum, and which is when taken a derivative with respect to CL and put equal to 0 will give us this result, that is CDI equals to 3 CD naught. For thrust required minimum, earlier we saw that thrust required minimum is inversely proportional to CL divided by CD maximum, but here power required minimum is CL is about 3 by 2 by CD maximum. And for CL by CD max for thrust required minimum, we saw CDI is equal to CD naught, whereas for power required minimum we are seeing CDI is equal to 3 times of CD naught. So power required variation with velocity is like this: net power required is this much, and CL is over 3 by CD maximum is this point at power required minimum. Okay, so design point is this, and with respect to this, the aircraft will fly at this velocity. Okay, so the velocity at CL is over 3 by 2 by CD max is the velocity with which the aircraft will fly with minimum power required. And if this is the velocity, then it should show us that that CDI and CD naught should be following this relation, that is CDI is equal to 3 times of CD naught for power required minimum. Let's see, CDI is like this, we know, and CD naught varies or say increases with velocity, and the intersection is CDI equal to CD naught. But for power required minimum, here is power required minimum. If we see at this point, CD naught is here, okay, which is CD naught is this, and for power required minimum, power required is this, minimum power required is this, and at this power required minimum, for this CD naught it is intersecting at this point, and for this CDI it is intersecting at this point, and here CD naught is equal to 1/3 of CDI. So say CDI is 3 times of CD naught, which is this relation. So from the graph we have clarified that it follows the relation like we did for thrust required minimum, where CDI is equal to CD naught. For thrust required minimum, the curvature is minimum over here and then increases again. Like here, the intersection of CDI and CD naught will be just below this minimum curvature. Okay, for power required minimum, the curvature minimum is here towards left. Okay, and power required and velocity variation, if we see for computing thrust required minimum, power required and velocity, y equals mx. So power required is this. So slope m, thrust required when drawn from origin to any point on the power required will be minimum when it will just be tangent to this curve. Okay, or when it will when this thrust required will be making the minimum angle, okay, with the horizontal, because tangent will give us perpendicular upon base. Tan theta is y by x. So thrust required will be power required divided by velocity, like this. Thrust required, power required divided by velocity. So minimum thrust required or minimum angle will be when there will be minimum when it will produce minimum angle, okay, minimum angle when the thrust required will be minimum, okay. So at any point, if we take the tangent, okay, if we intersect power required at any point with velocity, we will see an angle greater than this angle. This angle is the minimum angle, which is why we have thrust required minimum. And at this point, we will see CL by CD is maximum, which gives us the result CDI equal to CD naught, which is intersection of CDI and CD naught. And we will continue in the next lecture now.